Hello, and welcome to the last part of chapter 2, pardon me. This is the fourth part. And this is going to be about linear correlation. There's a couple of fancy words there. So we're going to start with defining the word correlation. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. So you could imagine that the price of buying a tank of gas and the number of gallons of gas, as one goes up, the other goes up, and as one goes down, the other goes down. So there's a direct correlation between those two numbers. A linear correlation exists between two variables when there is a correlation and the plotted points of a paired data set result in a pattern that looks like kind of like a straight line. It'll never be a perfect straight line. And I'll show you some examples here in a second. And the scatter plot, we already learned that word from the previous video. Is a plot paired XY quantitative data with the horizontal x-axis and the vertical y-axis. This is just your typical regular graph that you learned in an algebra class. And so here are some examples I want to show you. So this is a scatter plot of the rise of the sea level, and you can read this yourself. Here are the years, and here are the sea level in millimeters. And you can see of all these data points, it's not perfect. It's definitely not a straight line, but it definitely looks like there's a connection. As the years go on, the sea level seems to be rising based on this data here. So what we do is by the way, when we get to chapter 10, we'll actually do all of this. This is just sort of an introduction. What we'll get is we'll end up with something called a line of best fit. And your calculator has this way of doing this. It'll even graph it for you. And using math, we can actually come up with the slope of this line and the y-intercept. And if you remember y equals mx plus b from an algebra class, it's sort of that idea, but don't break into chills or anything like that. The calculator will do all of it for you. And you'll learn all about that when we get to chapter 10. All right, next up, we're going to talk about the linear correlation coefficient. Linear correlation coefficient. Linear correlation coefficient. And we use the letter R for that. And that measures how strong the connection between the x's and the y's are. If there's no linear correlation, then we'll know that. Now the strongest it's going to be, this R, will always be between -1 and 1. And its strongest correlation is going to be at 1 or at -1. Its weakest is at 0. That means if the linear correlation coefficient is 0, that means there is no connection between these two variables at all. A positive correlation means that as one variable gets bigger, the other also gets bigger. So for example, with the gas analogy, the more gallons of gas I buy, the more expensive it's going to be. So as one goes up, the other goes up. Now a negative correlation means that if one gets bigger, the other gets smaller. So for example, the more miles that I drive, the less gasoline that I have in my car. So as one gets bigger, the other one gets smaller. That's called a negative correlation. Now this next one, I actually did a lot of the work for us already. Your sheet is not going to have this graphic like this, but what I wanted to do, instead of wasting time to do this, I actually just plotted, here's my CO2, you can read through the problem, and see if there's a connection between, not CO2, pardon me, carbon monoxide, not dioxide, and tar, and that's in cigarettes. They want to know if there's a correlation between them, a connection between the amount of carbon monoxide and the amount of tar in a cigarette. And so here we have tar and carbon monoxide. So this is actually one big table broken up into 3 pieces like this. And what I did was I went through and plotted, so x is 16, y is 15, and so on. And I plotted all 15 of these points here, just so that we could see, do you see that there's kind of a linear correlation? It definitely looks like there's a connection there. And if I wanted to superimpose a line of best fit onto that, right, again, we would, of course, mathematically figure this out in a much more precise way than the way that I'm doing it now. And we could end up with a line of best fit. We have some below, we have some above, and so on. And so we're presented with the question, is there a linear, a relationship between cigarette tar and carbon monoxide? And this is definitely looking like a positive slope to me, meaning as the tar gets larger, the CO, or the carbon monoxide, also gets larger at the same time. So I'm going to say yes, the amount of tar increases, the carbon monoxide also increases. So A is the choice in this case.